We already knew that's the last one.
Morning, everybody.
Good morning.
Let's see here. Chapter, what are we on, 26? Chapter 26 homework is due this weekend, right? Chapter 26 was due this Friday. I think I originally put that in because of spring break and didn't want anything to do with spring. I put it on Saturday because that's what everybody's used to. So if you see a change, if you see a message that your due date changed, I moved it back. Get it done before spring break if you're worried about that. Otherwise, for today, that's normal. There's a problem on chapter 25, 26, something. One of the problems, 25? Yeah, where it just went sideways. It was not the question I wanted to assign. It was, anyway. So just watch the chalkboard video. I posted an announcement about that one. Watch the chalkboard video. It gives you the equation. Don't worry about that problem and knowing how to do it. Just get the right answer and move on with it. We are supposed to have an exam the Thursday after we get back from spring break. Past me was smart and made sure that the Monday after spring break, when everybody's hungover, was a lecture day in lab, which is good because we're behind because of jury duty. So I'll probably use that day to catch up and finish everything. Tuesday we're reviewing, Thursday the exam. I'll try really hard to make that exam on Thursday. If we can't make it because I talked too long about the eyeball or something, then I'm gonna try to speed run today. It's not gonna be pretty. If I have to push the exam back, I'll push it back to like the following Tuesday. Just one day, right? But we're gonna try and hit that Thursday. Keep things on track. All right. This is scary. I don't know, eyeballs freak me out just a little bit. And I really don't understand what's so funny about them. You can't see the dad joke smile underneath, I guess. Okay, yeah. Right? But in terms of an imaging system, it's a pretty neat trick of evolution. Does anybody know what the main focusing part of the eye is? Not the pupil. It's not the lens, it's the cornea, which is always funny, right? Because it's the lens, right? Actually, the biggest change in index of refraction is from air to the cornea. So that's where most of the light gets bent. Your lens, if most of the light gets bent and focused by the cornea, what does the lens do? Like, what's it for? Well, yeah, everything flips the image because this is refraction. Yeah, you actually are seeing everything upside down. So why does it look right side up? Because your brain just did it for you. Yeah, it followed gravity. Okay? But what does the lens do? If the cornea bends the light, acts as the focusing thing, what does the lens do? It allows for accommodation. So our eyes can actually focus over a very wide range of distances. And so the human eye has what we call a near point and a far point. The far point for a healthy, normal eyeball that doesn't need any correction is infinity. In other words, you can look at an object that is infinitely far away and still focus on it. For those of you that are wearing glasses right now who can't see far away, you have a problem with your far point. And you are what we call nearsighted. We'll get to this in a second. It all seems backwards. It's going to mess you up a couple times. Right? But a normal far point is infinitely far away. Now for our eyes, the physiology of our eyes, roughly 5 meters, 3 to 5 meters, somewhere between the 15 to 25 foot range, your eyeball will be completely relaxed and able to focus at infinity. Let's go to the other end. How far away can something be from your face and you still be able to focus on it? So I want you to do an experiment right now, okay? I want you to hold your hand at arm's length, like with your hand sort of out in front of you like this, where you can see your fingers. You can do it either way, it doesn't matter, okay? And what I want you to do is I want you to try to find a place in the room where you can look as far across the room as possible. And I want you to switch your gaze. I want you to look at your fingers, and then I want you to look at the far wall. And I want you to look at the fingers, and I want you to look at the far wall. Switch back and forth, okay, like once every couple seconds or so. And I want you to feel the muscles in your eyes. Concentrate on what your eye is doing. Just switching your gaze. Don't try to really move your eyeball. Just switch your gaze. Can you feel the muscles in your eyes working? Okay? That's accommodation. The muscles in your eyes, okay, these ciliary muscles, ciliary just means fine threads, are pulling on that lens and reshaping it in real time. And you need that, because if you do the same experiment, then don't switch your gaze. Just look at your fingers now. Look at your fingers, but sort of cast your attention to everything around your fingers. It should be slightly out of focus. You don't really notice that. And flip it. Now look far away, but kind of look at your hand. You can see it's not quite in focus, and there might even be two of them. Okay? Right? Our brains take all of the information about a visual field and process it. In other words, when I'm looking at people here in the front, okay, people in the back are out of focus. But then when I shift my gaze to people in the back, the people in the front get out of focus. But if I'm not thinking about it, I will think everything is in focus, right? Even when it's not. Our brain is integrating all the visual information and trying to build this virtual reality, right, that I live in, about what's in focus and what's not. Your lens is responsible, okay, for accommodating that entire range of focus that needs to take place. And what we're going to be talking about next is what happens when this system doesn't work properly. One of the things that happens as you grow older, there's lots of things that happen as you grow older, but one of them is that the lens itself becomes less pliable. It actually begins to stiffen up and actually crystallize in some cases. And the muscles in your eyes are unable to change the shape. And so you lose the ability to accommodate over certain ranges. And for certain people who are the old word in your life, old, right, okay? You might notice that they start reading things and they'll keep holding the thing that they're reading further and further away from their faces. They're losing the ability to focus up close. That's because their near point, the closest point at which they can hold an object and see it, okay, is moving further and further away from their face as their lens stiffens up. So do this. Take your hand, okay, same sort of thing. Start far away, start at infinity. Switch your gaze to your fingers, and then pull your fingers towards your face and keep it in focus as hard as you can. Just really try to focus, and you'll probably go cross-eyed, and now stop. How do your eyes feel? Tired, right? That's because you gave you just did a bunch of squats, okay, with your eye muscles, okay? This thing I had you switching back and forth, and then this, okay, was like a bench press, okay? It's like your muscles have to work really hard in order to focus on things that are up close. The normal near point for a human being is 25 centimeters. That's more or less a definition. Like, a person can comfortably hold something about 25 centimeters from their face, be able to focus on it, read it, whatever, okay? But as you get older, that near point begins to move away. Again, the near point is the closest point that somebody can focus on things. Kids have near points that are practically on their foreheads. Because if you give a kid a crayon and a coloring page and say, color the page, right? What do? Right? They get really close there because some stupid adult told them they had to color in the lines or some baloney like that, right? Okay? And so they're really concentrating really hard, right, to stay within the lines. And they put it like that close, right? That's because they can accommodate that close, right? You get to your teens and early 20s, you're at that normal near point of 25, and then by the time you get to 40, it's all over after 40. It's totally fun. My eye doctor's really mad at me because he's 3 years younger than I am, and he already needs reading glasses, and I don't. So he gets mad every time I go in. I'm like, sorry, doc. He's the guy that did LASIK on my eyes. I was like, you know. Okay, so how do we actually see stuff, right? These are pictures of the rods and cone cells that are in the fovea of your eye. The back, the imaging part of our eyeball, right, is there on the back. So we have this focusing power. We're going to talk a lot more about this system and how it focuses and stuff like that. We'll use our lens equations. But just quickly getting into these cells that are sitting here on our fovea. The rods and cone cells are responsible for taking packets of light, waves or packets, photons, and converting them into an electrical signal. Okay? The cone cells are responsible for color. And believe it or not, there's actually 3 main types of cone cells, each responding to roughly red, green, and blue wavelengths, which then get integrated into all the colors that we see, which is why computer monitors and everything use RGB color space, red, green, blue pixels and things. It's just corresponding to our eyes. And then you have the cone cells, which are responsible for people think black and white, but it's more contrast. It's more the ability to detect light in its various amounts. And so one of the things that rod cells outnumber cone cells by 10 to 1. There's I can't remember what it is, 30,000 rod cells for every 100 cone cells. We have a lot more rods, okay? And they are in a bigger part of that imaging part of the back of our eye. The cones tend to be packed, where's that, the retina, right, where the highest concentration of cells is. At night, notice this tonight or next time you're in a kind of a dark room or dark outside, we lose the ability to see color. Unless that color is very intense, like a red light at a stoplight or a green light or something like that. If you look at the bushes or something under moonlight or any of that kind of stuff, we lose the ability to see the color of those things. Because cone cells just aren't that prolific in our eyes compared to the rods. The rods are picking up light like crazy. Your eyes will dilate and the rods will get all happy. And you'll build up a chemical called rhodopsin in your eyeball, which helps the rods to even do things. We can have pretty good low light vision. Some people, not so much. My wife in particular is blind at night. It's just as soon as the sun sets, she can't walk anywhere. This is just scary again. This shot is really showing you what the cornea is, right? That cornea, that outer part of the eyeball, right? That interface between you and the rest of the universe, okay, is sitting right there. And it's that big change in index of refraction from air to the cornea, which has an index of refraction pretty close to water, believe it or not, that causes most of our focusing power in the eyeball. Now, getting into the optics of this, okay? We talked about that accommodation, and so now I'm showing you some ray diagrams that aren't necessarily following all those principal rays. We're not drawing 3 of them. These are more to give you an idea, okay, of what the lens is doing there. They're not showing very well the refracting power of the cornea here. Again, this is a conceptual diagram to give you an idea of what your eyeball is doing as we move objects closer and closer to our eyes. Unaided eyes, eyes that don't need correction, are converging lens systems. They're taking rays and they're focusing them down. We treat that system as a single lens. Now we know there's a lens, we know there's a cornea, but even eye doctors, they'll just put those two systems together so that it's not very complicated. There's really no reason to treat them as separate entities because together they form the refracting power that enables us to focus on things. So we treat them as one object for the purposes of doing all the physics, okay? I hate these pictures. These pictures are lying to you, but you'll see them all over the place, okay? Look at the top picture. If this is what your eye did, what would you see all the time? If light came into your eye and got focused down to a point on your retina, what would you see? You would see a bright point of light, okay? I don't like these pictures because they're implying, right, that the eye just focuses light down onto your retina. That is not what is happening. Your eye is forming an image. Where are the objects? Where's the front side of your eyeball in this lens system? It's everything out in the universe, right? Where's the back side of your lens in your eye? Inside the eye, right? Where towards the retina, fovea retina, all that back side of your eye, right? So the front side of the lens for eyeballs is always out there, right? And so images are being formed on your retina. We're not focusing on the retina. The light forms that image. The image comes into focus at the retina, which is, again, kind of what they're trying to show here in a simplified manner, but it's always bugged me that these physiology textbooks get it wrong, but that's all right. When you are nearsighted, you are overachieving in terms of the focusing power of the eye. A nearsighted person is focusing too much. Their eye, for whatever reason, now usually this comes about because of changes in the shape of the eyeball as you grow, okay? But the myopic or nearsighted eye has images that are forming in front of the retina. And so to correct that anomaly, we have to spread the light rays out. So what kind of lens does a nearsighted person wear on the front of their face in order to spread light out? Not a converging lens, a diverging lens. Okay? So every single one of you that's wearing glasses right now for nearsightedness is wearing a diverging lens on the front of your face. We'll get to that in a second. Okay? Farsighted people, okay, the people that need to wear reading glasses, that kind of stuff, they aren't focusing enough. Their eyes are probably squished up or done something weird such that there isn't enough refractive power to bring the focal plane into where the retina is. And so they need help getting the rays to focus. So what kind of lens causes rays to come together? That's the converging lens, right? So far-sighted people wear converging lenses. They basically wear magnifying glasses on their face. And then nearsighted people wear diverging lenses because they need help spreading out the light before it gets to their eye. And people that are both nearsighted and farsighted wear bifocals or progressive lenses, as it were, because they need to correct both things, and it's really annoying. Here's a simulation of what it looks like to be farsighted. Okay? Things up close are difficult to focus on. Okay? And in fact, you lose the ability to even see things up close, right? Which is why your parents or your grandma or something like that might put the reading glasses on to work their phone or their remote or something. They can see just fine the TV across the room, but it's that up close thing that they're having trouble with right here, right? So let's talk about what's going on in this system, okay? and how to correct it and how we talk about all of these corrections. Because the mathematics we're going to use is the math we already know. It's that set of conventions and our lens equation / mirror equation, however it is you want to think about it, okay? So, what is the manifested problem for a far-sighted eye? Remember, let's go back to near point. A far-sighted person means what? They can see far, right? Far-sightedness means they have the ability to see far away. The implication is they can't see close up. So what is broken in this system? Is it the person's far point or near point?
Near.
It's the near point that has trouble. So catch that, right? A far-sighted person has a trouble with their near point. The near point is not 25 centimeters, it's bigger. Okay. So, when we put a corrective optic into the system, meaning a pair of glasses or a pair of contact lenses, okay? The whole purpose of the corrective optic is to create an image at the place where the person can naturally see it. What do I mean by that? In the top picture shows the problem, right? The problem is that this image is forming behind this person's eyeball. They can't focus on it. The object, right, is inside the near point. The near point is where they can see things. So notice when we put the converging lens into the system, we're going to generate what kind of image? It's a virtual image. So this is what a lot of you were struggling with seeing yesterday in lab, okay? Right? We're forming a virtual image. It's a magnifying glass. It's a magnifying glass with the object inside the focal length. So you're always going to get a virtual image. But where are we putting the image? Are we putting it at the normal near point of 25 centimeters? No. We are putting the image at the person's natural far point. I'll do an example with numbers here in a second. But critical to getting these kinds of corrective optics questions correct, that was the Department of Redundancy Department. You need to make sure you understand the concept. A far-sighted person's fill in the blank is broken. Near point. It always screws me up. Okay? A far-sighted person's near point isn't 25 centimeters. Whatever it is, that's where I want to put the image. The object distance is 25 centimeters. You want the person to be able to put an object at a normal near point with 25 centimeters and then give them an image at the place where they can see it. So if somebody has a near point of 1 meter, okay? That means anything that comes within 1 meter to their face, they can't focus on. We want to put an object at 25 centimeters. We're going to generate the image out here where they can see it. So let's do that calculation. I went ahead and said, here's the far-sighted case. So let's say an optometrist measures a person's near point to be 57 centimeters. Really quickly, what's the difference between an optometrist and an ophthalmologist? Close, okay, that's a good rule of thumb, but an optometrist is the doctor responsible for correcting vision. You see blurry for any reason, optometrist. An ophthalmologist is responsible for the health of your eyes. So scratched corneas, eye diseases, problems with your retina, problems with your pupil, problems with your lens, those are all ophthalmologist's territory. An eye surgeon would be an ophthalmologist, not an optometrist. Just so you know, they're both doctors. Okay, so the optometrist measures, okay, the near point of this person be 57 centimeters. We know because this near point is not 25 centimeters that this person is farsighted. Right? And so we want to calculate the focal length of lens that's necessary in order to help this person see correctly. In the farsighted case, we set the image distance to be equal to the person's far point. Again, we want to put the image where they can see it. Why did I put a negative sign on that image distance? Where's the front side of the lens? This is the front side, isn't it? Okay? And we're going to put that object there, and then we're going to form an image on the same side of the lens as that object. Notice, I am not talking about the image that hits their retina. I really don't care about that, okay? We are creating an image from the corrective lens we're putting on the front of their face, okay? Out on the same side as all the objects, out there in the universe, right? The physics of the eyeball will work itself out so that real rays do hit the back of the eye, okay? Even though they're looking at a virtual image, real rays will strike back of the eye in proper focus. That's all handled behind all the math. But we put a negative sign on that image distance for corrective optics because the image is on the same side as the object. The object distance is 25 centimeters. Again, for a nearsighted person, we want them to be able to hold a book or a phone or anything else at a comfortable 25 centimeter distance. And then we can calculate what the focal length is going to be. Right? Focal length is inverse of distance to the object plus 25 plus 1 over a negative 57 inverted gives me 44 centimeters, a positive 44 centimeters. Okay, so what does a positive focal length mean? What does the sign convention say about positive focal length? It's a converging lens. Does that track with all the pictures I showed you? Yeah, right? Farsighted people don't focus enough. Their eyes don't focus enough. And so we need to help them focus more. So it's a converging lens. Focal length is not the natural unit that optometrists use to talk about the lenses that they're putting in people's eyes. Instead, they use an idea called refractive power. Okay? The refractive power is the inverse of the focal length. So what optometrists are doing is they're not inverting their answers, okay? You know how we have to do 1/overs and 1/overs and then finally invert our answer to get the focal length? Optometrists dispense with that. They just keep it like this, and this is 2.27 inverse meters, which is called a diopter. So if you wear glasses and you've ever been given the prescription for your glasses, there'll be several numbers on there. But the numbers will always be indicated in refractive power or diopters. So a -4 would be for a nearsighted person, okay? And a positive number, +2, would be for a farsighted person. Positive meaning converging lens, negative meaning diverging lens, and then that power is given as an inverse meter. Okay? I think they do that just so they don't have to keep inverting, but that's on them. We'll go with it. Just realize that a diopter is another name for 1/over a meter. All right, we usually in physics go for the focal length of the lens that's necessary. So this person would need to go down to like, the local drugstore, because you can just get reading glasses without a prescription, and get a reading glass that would be in the +2 range. +2 or 2.5. There's actually quite a bit of subjective feeling that comes into this. As many of you experienced yesterday, seeing a virtual image is a very subjective experience about like where it's located and how big it is and all that kind of stuff. So that's why if you've ever been to an eye exam and the optometrist has like measured what, like there's computerized ways to do this. If you've ever been at a machine and you're staring at a hot air balloon or a ship, a sailboat or something like that, that computer is actually measuring the curvature of your cornea and predicting exactly what your prescription should be. But 9 times out of 10, 90% of the time, if you hand that prescription off and get glasses just made from what that device tells you, a person will complain. And they'll say it doesn't feel right, or it looks blurry, or whatever. So that's why they'll sit you in a chair and they'll put the funny big thing in front of you and they'll go 1, 2, 3, 4, 5, 6, right? They're subtly adjusting in quarter diopter amounts what the computer told them to do, okay? Because they're trying to see what you as an individual and how your brain is interpreting the virtual images, how it feels about what it sees, right? So if you've ever been to an eye exam, you know what I'm talking about. If you've never been to an eye exam, go get one. Seriously, eyeball health is important, okay? And you want a record of how your eyes have changed over your lifetime. And knowing what it was like in your teens and 20s will help you when you are in your 40s. Okay? It will help the doctors figure out if something's going wrong, if something's going right, all that kind of stuff. So getting an eye exam is pretty important. It's right up there with teeth. I mean, they're much better than going to the dentist, but anyway, yeah, go there. Oh, another thing, if I can be your father for just a second. Stop looking at your screens for more than an hour at a time. Like seriously, I'm not talking about the content of what you're viewing, that's on you. I'm talking about if you got a screen this far in front of your face for an hour, what are the muscles in your eyes doing when you're focusing on something up close? They are tensed. Remember this exercise where I said bring it in? And you went, to look at something that close all the time has your muscles constantly in tension. If I told you you had to hold a 10-pound weight out at the end of your arm for an hour, what would that feel like when you were done? Assuming you could even make it. It would hurt. Your muscles would be tensed for an hour, right? And then as soon as it's able to relax, it'll go, and Charlie horse it all over the place, right? Okay? That's what's happening in your eyes if you focus on something like that. The medical advice is every 15 minutes, give your eyes a 30-second rest. It's pretty amazing. All they need is 30 seconds. And how do you rest? How far away does something need to be for your eye to be totally relaxed? 15 to 25 feet away. So every 15 minutes, just look up. Touch ground. No, listen. Just look up at something across the room. Close your eyes for 30 seconds. Set a timer so you don't fall asleep. But when you close your eyes naturally lose focus and will reset to the infinite amount. Okay? So, making it a practice. I know that, like, if I've been sitting there making up your exam for an hour, okay, I'll actually get up because I'm old and I need to stretch my legs. But I will use that opportunity to also look away, right? I'll go find somebody to talk to. I'll go walk down the hall. Like, it's just, your eyes need the break, okay? And yes, if you're sitting there and you're getting a headache doing your physics homework, there's 2 problems there. Physics homework and the fact that you are like focusing on a screen or the page or whatever, right? Okay? And your eyes just need that relaxation break, okay? So keep that in mind, right, as you go about your day. Try to give your eyes a chance to relax. I do it about once every hour because my watch yells at me when I'm not standing up, right? So that's when I remember to do it. Okay, so let's talk now about nearsightedness, because this, I think, is going to hit a little closer to home for the age groups that are represented in this room, okay? This is not so much a simulation, but a really dodgy picture of what it's like to be nearsighted, okay? Things look nice and clear through the glasses, okay? But everything else looks blurry. This was me until I got LASIK for my eyes. I got LASIK at 43 years old? Something like that. Before that, the far point, the furthest distance I could see with my left eye was about that close. Everything past within about 2 or 3 inches of my nose was blurry. Okay? Now, if I took my glasses off and I needed to see something up really close, I was your man. The glasses off, I could focus really good on it, okay? Because my eye was just that messed up. My right eye was about that far away. So anything beyond that, okay, was basically just totally blurry, out of focus, just like that, okay? And glasses, I had pretty thick lens on the left side, fairly thick on the right, okay? They weren't bottle caps by any stretch of the imagination, but for those of you that know your prescriptions, my left was a -7, and my right was
So bad.
-5.5. So yeah, I was pretty useless without my glasses.
He brought them the other day to show us.
Yeah, I showed you, right?
Oh, we mentioned him, yep.
I know tricks, okay? And one of the tricks you can do with glasses, it does make them more expensive, but it makes them more comfortable. You can get high index materials. There's polycarbonate materials for glasses that they have such high indexes of refraction that they can be made thinner. So my original glasses were pretty thick in high school, but as I got a job and medical insurance, I was able to afford the more expensive lens. Number one, it was made out of polycarbonate. If I'm going to put anything near my eyes, it's going to be safety glass, or safety plastic in this case, okay? Number two, it was going to be high index, meaning it was thinner and lighter so that my glasses didn't do this on my face. Because I had that heavy lens on this side and they would do that. And then I would make sure that there would be we're going to talk about this in the next chapter, I'd make sure that there would be an anti-reflective coating on them. More about that later. Okay, anyway, so this is what it looks like to be blind. So what's going on? Again, right, focusing problem, but in this case, focusing too hard. So we know, theoretically or conceptually, that we're going to be putting a diverging lens in this system. A nearsighted person has a depressed far point. In other words, speaking my language, the far point is not infinity. You're overachievers and depressed. You are not supposed to take any psychological implications.
Are you sure?
Yes. Okay. So what is the object distance for a far-sighted person? The real thing that they're trying to see. How far away is it? It's infinity. I could not see anything past my hand, right? About 4 inches from the front of my face. That means everything past that was effectively infinitely far away for my eye. My far point was so depressed, right, that infinity for me was everything past that point. And so the object distance when you're correcting for nearsightedness is always infinity. We're trying to take far away things and put them in focus for nearsighted people. But where can nearsighted people see things? At their far points. My left eye could not see anything past here. So the corrective optic would put the image for distant objects, infinitely far away, at my far point. This is what the math looks like. I tend to just draw a real quick diagram. Okay, that's an eyeball, that's the lens, and then my object for farsightedness, if nearsightedness is really far away, my object distance is infinity. I have a far point right here, and this is where my image is being formed. It's just a way for me to visually lock into what's going on here. So I know my object distance is infinity. I know my image distance is going to be the negative far point distance. Why negative again? It's in front, right? I'm forming an image in front of this lens, the same side as the object. I can't say this enough. When you're correcting a person's vision, you are generating an image where they can see it. Whatever that far point or near point is, you want to match their far point or near point. In the case of nearsightedness, myopia, you want to put images at their far point. So let's say that a person's far point is measured to be 45 centimeters. That means that they cannot see, they can't focus on objects that are further than 45 centimeters from the front of their eye. We want to find the focal length of the lens, okay? 1 over f equals 1 over the same standard equation, right? Okay, so the focal length is going to be 1 over the distance to the object. 1 over positive infinity plus 1 over, and I'm going to put in negative 45. I'm going to invert all of that. This math is pretty easy, because what's 1 over infinity? Not infinity. What's 1 divided by a very big number? Close to 0, right? Okay. So 1 over infinity is 0, and then 0 plus that. So basically, all I've got to do is invert 45, right? Or just invert 1 over 45, which is 45. It turns out that the focal length of the lens that you need is the far point distance, with a negative sign on the front of it, okay? So there's the focal length of the lens that this person needs. The refractive power in diopters would be negative 2.2 diopters. Capital D is the symbol for diopter. And away we go. Again, the hard part with corrective optics is the concept that a far-sighted person has a problem with their near point, and that you want to put the image at a far-sighted person's near point. And for a nearsighted person, the problem is their far point, and you want to put the image at their far point. What is the object distance for a nearsighted person? Infinity. We want to take things that are infinitely far away and get them in focus for them. What's the object distance for a far-sighted person? It's 25. We standardize on 25 centimeters. The homework is annoying because the author insists on you making a correction for the distance between the lens of the glasses and where the eyeball is. So just be careful about that. The author, like in a couple of the homework problems, they'll say like the lens is 2 millimeters from the eyeball, but then the person's, I don't know what it is, near point, okay, is 20 centimeters from the eyeball. The lens is where you've got to measure everything from, right? So what here then is going to be the image distance? 18. So just realize that if they give you a distance between the lens and the person's eyeball, you've got to do a little bit of a distance correction, okay? Because again, everything's referenced from the lens. If the problem says they're wearing a contact lens, or they say it's wearing glasses and they don't give you the distance, ignore it, it doesn't matter, okay? I wish the authors of these books would just not even worry about it's such a minute difference. Most people don't even notice it when you give them the correct refracting power for that. All right. Let's do a quiz. Woo! But before we do that, I want to point out something that might have flown under the radar about the kinds of images we were just talking about in both cases. Nearsighted and farsighted, what kind of image are those people looking at? They were virtual images. So those of you wearing glasses right now to see me, you're staring at a virtual image. You are in virtual reality. And people that wear reading glasses, well, they see virtual images too. Are virtual images any less real? Like, does real light hit your retinas? If you're looking at me with glasses right now, does real light hit your retinas? Yes. Real images are being formed on your retina. It's just that those real images, those light rays, are quote unquote coming from virtual images, constructs in your brain. For those of you that struggled yesterday in lab to locate that virtual image, okay? It didn't matter if you were wearing glasses or not, the struggle is equal. It's just that with your glasses, you've gotten used to the changes in depth perception for objects that are far away. So if you're wearing glasses and the image is being formed right here for you, you still have all of that depth perception because you've learned. Your brain has learned how far objects are, how fast they're moving within your virtual reality. Those of you that wear glasses know that it can be a little bit of a trip when you get a new prescription for your glasses. You'll put them on and things will be kind of weird. The world will look a little bit bent for a while. And you might even get a little bit like motion sick, or you'll get tension in your head or whatever, right? That's your brain body trying to come to grips with the new reality of the virtual image that you're seeing in front of your face. The good news is that it's in focus. Right? So, there you have it. Okay, astigmatism. So, we've, I, and your book, and the conspiracy theory of physicists around you that have been neatly sweeping all of the hard stuff under the rug for you the entire semester. There's more going on to focal lengths of eyeballs and lenses and things like that. We've talked about lenses that have a single axis. But in fact, lenses can have multiple axes of focus. We divide these into two general, like vertical and horizontal directions. But those vertical and horizontal directions can actually rotate around. In this picture, they're really just looking at the vertical and horizontal because it's easier to understand. But astigmatisms can be very, very complicated. So an astigmatism means that your eye focuses light differently in the horizontal plane than it does in the vertical plane. Your vertical plane might be perfectly in focus, but your horizontal plane can be totally out of focus. This generally gives people with really strong astigmatisms will complain about, without their glasses, things look squished or football shaped or something like that. That's a real extreme case. Most people with astigmatism just notice that there's a slight blurriness around things. The astigmatism of your eye can change throughout the day. So waking up, your eyes are generally a little bit wetter because they've been closed for a long time. and your astigmatism can be very light, and then as they dry out during the day, and different parts of your cornea dry out or whatever, you can actually get a rotation of those focal planes and your astigmatism can increase. You can change the astigmatism of your cornea by simply blinking a lot in some cases, okay? So astigmatisms can be rather difficult to correct, especially for people that prefer to wear contact lenses. For glasses, it's not so hard, but for contact lenses, it can be a little bit of a trip. The idea is you're going to correct only the focal plane that needs correcting. Sometimes both, usually one or the other. To do this, they will add a third number to your correction on your prescription called the cylindrical correction. So you'll see 3 numbers. First 2 are all about the refractive power. And then the third one will be a positive or negative, and then a number that's usually an angle, even though they don't specify the units, okay? And it'll say cylinder or CYL next to the number. For the person making the glasses, that's a clue to them about how much they have to rotate the angle at which they are applying the corrective axis for your glasses. If you have astigmatism and you're wearing glasses right now, you can actually kind of take them off your face and rotate them, and you'll see stuff go out of focus, okay? Or it'll look funny as you kind of rotate. If you don't have astigmatism, there shouldn't be any change in that rotation, okay? But if you do, there should be a slight change, a slight blurring, fuzziness, things going in and out of boldness. Like people with astigmatism will often say that they don't see, things look faint, but when the astigmatism is corrected, it looks clearer or bolder or more contrasty. None of that's true, it's just how their brain is interpreting how the light's hitting the eye. So that's what an astigmatism is, and the cylindrical correction tells so knowing what I know about optics, I've been given glasses that I know that they got the angle wrong. Because I put it on my face and I can see that there was an error in that. I could just tilt my glasses. If I wore my glasses like this, it was great. And I had to hand them back and say, the person that made this got the angle wrong. And they're like, what do you mean? I was like, I have a graduate degree in optics, okay? I'm an expert in this field, and I'm telling you right now, when they made these glasses, I can tell you that they rotated, the machine was offset by 90 degrees. Like I could just tell them what the angle was. Because I could see, they knew I had to hold my thing like this, right? And so they would run back and put it in their machine and come back and go, oh, you're right, sir. And I was like, don't question me in this. You can question me in anything else, but this I know. So yeah, that happened more than once to me, that they would get that angle wrong. But I'm really sensitive to optical aberrations, to problems in optics. Like in the windshield of a car, I can see where the windshield wasn't quite made correctly, because I can see the wiggle, and everybody else is like, what are you talking about? I'm like, right there, this little spot. I also see dead pixels. I can see them from a mile away. Like, my family makes fun of me because I'm constantly cleaning the windshield of my car. I'm not being excessive compulsive or anything. I just want to be able to see. And if a bug has splatted itself on the window, what am I focusing on now? Not the road, the bug, right? So I'm like, get it off. So like every time we stop for any reason, I'm cleaning the windshield. And the kids just groan. They're like, oh, Dad's gonna clean the windshield again. Windex is a perfect fluid. What can I say? Actually, the other stuff is better. What's that stuff called? Comes in a spray can. It's a foaming glass cleaner. What's it called? Oh, spray.
The one in the can?
Yeah.
The white cap on it? It's so good.
Spray away, spray something. Yeah, it's really, really good stuff. It's more expensive, but man, if you want an optically clear piece of glass. Whoa. Okay. No, okay. I want to talk about microscopes and telescopes, okay? But I'm actually going to skip over microscopes more or less completely.
What?
I know, we don't have time. I know all the biologists in the room just died, right? But like, telescopes are where we're kind of going with cosmology and modern physics and all that kind of stuff, okay? So, but let's talk really quickly about why we think small things are big and big things are small. It's a trick of your brain again. Brain's always involved, isn't it? So if we went outside and we looked down towards the fountain, right, we would see people down by the fountain, right? How big would the people be? Yeah, maybe teeny tiny people, right? Okay. But we don't say, oh, that person shrunk. What do we say? They're far away. Why do we do that? Because they are far away, Mr. Balogh. We have a sense in our brains of how big humans are, right? And so to see a human that's not that size implies distance, okay? The same thing happens in reverse when things are big, bigger than we expect them to be. What's happening is if an object or even an image takes up more of your field of view, so our field of view is roughly 180 degrees. Like we can see out here into our periphery pretty well, depending on our eyes, okay? But generally for human beings, it's 170 to 180 degrees, okay? If something is taking up a lot of those degrees, we either say it's really big or really close, depending on what our subjective experience with the size of things is, right? We know that cells are itty bitty teeny tiny, can't see them with our eyes. So when we look through a microscope and we see a big cell, we say that we magnified it, right? Okay, so it's the relative size here that's giving way to this somewhat illusion that something is bigger. So like when you look through a magnifying glass and you're looking at that virtual image, okay, we say it's bigger. Why do we say it's bigger? It's because it's taking up more of our field of view. This is something called angular magnification, okay? And the angular magnification of a magnifying glass is the near point divided by the focal length of the lens. I'm not going to bother to write that one down. You might see another equation that's 1 plus the near point divided by the focal length. That's because with a magnifying glass or a microscope, you can focus on something in the microscope with your eye either completely relaxed or completely tensed. Most newbies using a microscope will do the tensed version. When I gave you the magnifying glasses and we were playing around with it, I guarantee most of you were doing the tensed version of that, okay? It takes practice, and it's a learned skill to be able to fully relax your eyes while looking through a microscope or a telescope, and then adjust the focus. But it can be done. I learned this trick early on in my college career, and I was taking biology and micro whatever stuff, right? Because I could go in the lab, I could stare through the microscope for hours on end and draw the pictures, do whatever it is I needed to do, and everybody else was getting headaches. I'm like, why aren't you getting a headache? I'm going, nerd. Right? I had already learned growing up with a bunch of telescope people around me. My dad was a big telescope guy. I learned how to relax my eyes so I could look through things for long periods of time. Same thing with a camera. Any optical thing, we tend to try to maximize our magnification, and that means a tensed eye. But you can actually relax your eye. But this Mississippi, we know the writing isn't supposed to be that big, right? And so we would say, well, it's been magnified, bigger than it should be, but it also appears closer. It's not closer, right? It's a virtual image. What's happened here is it's taking up more of our field of view than it should. And so our brain is trying to interpret what's going on here, and it's either saying it's going closer. The people can't be impossibly little people, they just must be far away. In a microscope, usually more than 2 lenses, but we'll just very quickly go over a compound microscope, which is 2 lenses. Again, you have an objective and an eyepiece. And where's the eyepiece? Which one is that closest to? The eye. The objective lens is closest to the object. Good, so you always know, right? But you can see here, we're using the objective lens to make an image, and then the eyepiece is looking at that image, using it as its object to create another image, which is a virtual image, right? And that's why you get a flip in a microscope. You'll get the, everything will be, you have to move everything backwards in a microscope because the image has been flipped once, but then hasn't been flipped in the eyepiece. This is actually fairly complicated stuff, but the main difference between a telescope and a microscope is how close you put the object to the objective lens. In a microscope, you put the object you're trying to see as close to the focal point of the objective lens as possible. But in a telescope, how far away are the galaxies and planets and moons and all that kind of stuff? Infinitely far away. Whatever the focal length of the objective lens in a telescope is, your object is infinitely far away, okay? But again, it's a compound system. The nice thing about a telescope, for objects at infinity, the light rays are all coming in parallel, which means that the image will always form at the focal point of the objective lens. And so, for a telescope, the length of your telescope is going to be the sum of the focal length of the objective lens plus the focal length of the eyepiece. It will always be that. So if you know that your objective lens has got a focal length of 50 centimeters and your eyepiece has a focal length of 15 centimeters, then you know the length of your telescope is going to be 65. The distance between lenses has to be 65 centimeters. There's no easy way to do that with a microscope. There just isn't. When you calculate magnifications, the magnification of a telescope turns out to be the focal length of the objective lens divided by the focal length of the eyepiece. If we had had time in lab, I would have had you build telescopes and asked you to get the maximum magnification out of your telescope. How do you get the biggest number out of that magnification right there? Smallest denominator, biggest numerator, right? So you want big lens for the objective, and you want a really small focal length for the, not size of lens, but focal length of lens for the eyepiece. The problem is that the higher the magnification, usually meaning the smaller the focal length of the eyepiece, the harder it is to actually see through the telescope. Have you ever picked up a pair of binoculars and they've been so magnified that you kind of have to hunt around to be able to see the image in there? That's something called eye relief. An optic with a big eye relief means there's a big zone where you can see the image that's being formed. But usually the magnifying power is low. The higher the magnifying power, the shorter the eye relief gets and the harder it gets to actually be able to find the sweet spot where you can see the image that's being formed. So there's a trade-off there in telescopes when you're trying to design them. The telescopes I've been describing so far are called refractors, meaning that they use lenses to form the images. Refractors are really, really good at making sharp images. They're not so good at collecting light. The more light you can collect, the further away you can see distant objects. The lenses get very expensive as they grow in size. And there's a physical limit to how big you can make lenses. The largest lenses and telescopes in the world top out at around 2 meters in diameter. Okay? So just a little bit taller than me, about the height of a 6-foot person. Those lenses, if you make them any bigger than that, they begin to sag under their own weight and it distorts the shape of the lens. So you have to get really clever with materials and all that kind of stuff, but there's a limit as to how big we can make the lens in a telescope. That limit can be surpassed if instead we use a mirror. So in a reflecting telescope, we are only limited by how big we can make the mirrors, and we can make really big mirrors. I think the biggest single mirror telescope has a diameter, I think, of 30 feet, like 10 meters, okay? But there are telescopes with diameters, physical telescopes that measure diameters in like 45, 50 meters, like huge, huge. Those surfaces are broken up into smaller mirrors, honeycomb, hexagons, okay? Where each hexagon is independently controlled to focus. It's really, really cool. But if you're clever and you use a little bit of computer science and a lot of mathematics, you can actually pair telescopes together that can be separated by kilometers. So you have a mirror telescope over here, mirror telescope over here, mirror telescope over here. You get these things called very large arrays, and you can effectively make telescopes that have simulated or effective diameters measured in kilometers. The light gathering power of a kilometer's worth of telescopes. It's really cool. It uses something called adaptive optics. Radio astronomers can pull off a similar trick, but they can make telescope dishes, the radio antennas, that are basically the diameter of the Earth. Not quite, because we haven't put one at the North Pole. We put one at the South Pole. But when you integrate the data from all of these radio telescopes at different latitudes around the Earth, you basically get a radio telescope that's got a dish the size of the Earth. It's really cool. It's really cool. But anyway, if you've got a physical mirror, light comes in, bounces off the mirror, gets angled either out the side in something called a Newtonian design, where it goes to an eyepiece, or something called a Schmidt-Cassegrain design. These are named after people who invented them. That goes out the back. The Hubble Space Telescope and the James Webb telescopes are not quite Schmidt-Cassegrain, but they're really closely related to that. And you can see there the primary mirror of that telescope, the big shiny. Now, the thing why telescope mirrors can get so big, we can build the substrate out of whatever we want. Steel, carbon fiber, doesn't matter what, cardboard, whatever, okay? Don't use cardboard, it doesn't work that well, right? And then all we gotta do is we need to just put a thin coating on the surface of that. That was my specialty, was developing coatings for optics, okay? In this case, use X-ray telescopes, not visible ones.
So why does, like with James Webb, why do they have a gold coat?
So they put a gold coating on there because it looks gold to us, but the James Webb is trying to reflect infrared light. Okay, so we see the sort of the yellows, reds, and oranges in the reflection, which is why it looks gold. It's not gold. There's other gold parts, coated parts of that spacecraft. Reflectors will be more squat. They'll be kind of bigger, but shorter. Unless you want to go really big. This is a door. Okay, right, for this telescope right here. The Hubble Space Telescope, right, is about the size of a school bus. Its primary mirror is about as tall as I am, right? And the Hubble Space Telescope has completely changed how we perceive our universe, okay? Hubble Space Telescope and the science it's reported, and James Webb seems to be doing it about 10 times faster than Hubble is. Like, the number of times we've had to update our knowledge of how planetary systems form since James Webb's launched, I think is now measured at least 5 times, okay? The Hubble rewrote our understanding of how the universe started 3 times in its 20 years, first 20 years of work. So, like, we are going to get a lot more into the impact of telescopes on our understanding of how the universe works, but we'll do that after we get through modern physics and relativity. That was the end of whatever chapter I'm on, and we'll start the next chapter on Tuesday.
You like that?
So I'm still a day behind.